Why didn't the recording started? But it says stop record. So
Yeah. Hello, ladies and gentlemen. Sorry, so it will only be 30 seconds of a little announcement. So on Monday, we start together for 4 weeks. And I will do only 3 classes, so 3 hours of class per week. So on Monday mornings, I have highlighted this on Canvas. We will start, sorry, I'm unable to use your PC, here it is. We will start at 10, okay, guys? So we will do 1 hour on Mondays, 10 to 11, and then 2 hours on Tuesdays, which is always 12 to 2 p.m., okay? Then the workshops are as normal. Is this plan okay? Yes. If at any point we notice it doesn't work, we can always change back to doing the 2 hours on Mondays, okay? That's it. I'll leave this class.
just so please remember, if you come at 9, don't leave. Don't leave. Just remember that it's 1 hour late.
Class is at 10 on Monday.
Okay. So today, very quickly, UV and IR. As I said yesterday, UV and IR are not, they don't require so much time as mass spec and NMR because UV or organic, unless you're really focusing on some fluorescent, phosphorescent, you need to calculate something else with UV. For the organic identification of compounds, UV is good only for, let's say, if there is an absorption band on the UV, you normally say yes, probably there are other aromatics or strongly conjugated double bonds. It could be that it's not aromatic, but it absorbs because there are some conjugated double bonds. Apart from that, also for the workshops and exam, you don't need to mention that on the exam. You mention only if you see a band, and you say if there is a band, also checking the other spectra, either confirming or not that you have or not aromatic. You use also the UV. On the IR, I think you should know probably IR. I'll leave you these slides, but they come from the class material, okay? So, for instance, if you have something like that, normally there is an aromatic. Also for the AR, I think it's probably the technique that you use the most since you start on the first year. So you know that IR, you cannot assign a molecule, but you can just see some specific functional groups. There are tables for IR. You don't need to remember them all, but you need to remember how to interpret and how to use the tables. So probably the most important things that you want to check on the IR are certain specific groups. Something like the stretching and the bending of aliphatics, which are over 3,000. So when you see a large peak over 3,000 is aliphatics. Over 3,500, 3,600, you can find alcohols and amines. Remember, from the shape of the peak on the amines, you can also tell me it looks like a primary, secondary, tertiary. For the alcohol, if it's a big, large, broad band, around 3,500, 3,600, if it's very broad, it could be a proper alcohol. If it's a little slimmer, it could be a carboxylic acid. But you will also cross-reference all the other spectra, and you can tell me something more. But for the IR point of view, another big thing is carbonized. Strong, intense peaks between 650, 680, 1680, and 1700, you can find all the carbonates. You can also, according to the different position, distinguish if it's an ester, an amide, or ketone, for instance, okay? Also, in this case, you will use the other technique to confirm or not. So, the combination of all these techniques that you've seen so far is what you need to have, what you need to do for the exam. So you will see now a couple of proper exercises. I will give you. Normally there is IR on the top and UV on one side, and then there are mass spec, carbon NMR, and finish with the proton NMR. You start from wherever you want, but probably the most important thing you have to start with is the calculation of the degree of unsaturation. If you remember how to do it, I hope so. It really helps, because if you calculate the degree of unsaturation, we did that last in the second year as well. But if you calculate the degree of unsaturation, you can get a clear idea of if you have double bonds, if you see an oxygen, if you have a carbon, or if you have aromatic groups. Remember that each benzene ring counts for 4 unsaturation. If you have 4 unsaturation and you see a big bundle of the UV, probably there is an aromatic group. Let's say that you have 4 unsaturation according to your calculation, but you see also an oxygen. If you have a benzene ring, a 6-member ring, aromatic, 4 unsaturations are for that one. If you have all these 4 unsaturation, then oxygen cannot be a carbonate. This is something that you want. This is what I mean sometimes with cross-referencing, and go for one technique to the other and back to the previous one, okay? So you have to always use them all at the same time to either confirm or not the presence of certain functional groups, and then eventually to build your structure, okay? So this is a typical exercise. IR on the top, mass spec. Remember all the most important, most recurrent peaks. Carbon, which normally, as we said yesterday, I try to every time to give you the depth as well, because the depth really helps in understanding if you have methylene groups or not. And then you have the proton NMR. Proton NMR sometimes can tell you almost immediately if you have certain groups or not. Sometimes it gives you the final formula, just the proton NMR, if you are good enough in interpreting the proton NMR. So, considering that you have to comment on all the different techniques, you start from wherever you want, but in the end, in your report on the exam, you need to give me few lines of each of the spectra and tell me, I see from the IR these and these peaks, so I think I have these and these functional groups. The mass spec tells me that the peak at that one belongs to that group. Eventually, you need to get, for the exam and for the workshop, you need to get a sort of all considered. So you wrap up all your considerations. And you tell me, according to the fact that on the mass spec I see this, on the IR I see that, on the carbon I see this number of carbons and blah, blah, blah. This is the final molecule. Writing down all the final molecules without commenting, just because you're guessing, it's not going to give you so many marks. On the other hand, sometimes even if you don't get the final molecule perfect, you can get very good marks because you actually maybe interpret quite well some techniques, but you didn't interpret well enough to distinguish and to assign the proper final molecule, okay? So looking at this one, what can you tell me? Start from the IR. It looks like there's a carbon. So I think you cannot see it, but okay. Move it up here. So you start from the formula normally. Start to calculate the degree of unsaturation. If you don't remember, don't worry, I will give you the final formula above. Hopefully you can calculate the degree of unsaturation. Remember that a saturated molecule, something like, let's say, ethane. Anyway, is the number of carbon and the number of hydrogen are in a certain sequence, something like normally is C, the number of carbon is Cn, and stands for the number of carbons, and the hydrogen is 2 by n plus 2. But we will see with a proper calculation. So again, if you can calculate the number of concentration, we see a carbonate. We also see on the IR, that we have some aliphatic groups. Okay, because we have that peak, the large, quite intense peak around 3,000. So that's the stretching of CHs of aliphatics. You have 12, 40, which if you remember from the tables, or if you check on the tables, 1240 normally is a carbon single bond oxygen, but it could also be carbon double bond oxygen. But the stretching of the sigma bond, and each carbonyl also has a sigma bond, is around that area. So if I'm highlighting these numbers, there is a huge chance that you have to comment on all of them. So please try to comment on all the numbers that I'm highlighting. Let's go for the mass spec. What do you see on the mass spec? Is there anything that jumps out that says, okay, I get this, normally this number gives you this functional group? You remember what the 43 is? It's quite a recurrent one. If you see it is a signature of a specific part of a molecule. CH3 is the acetyl, is the acetyl ion. Okay. So if you have 43, 99.9% of the times you have a CH3 connect to a carbonyl. That also means if you see the CH3, okay, you see the 43 on the mass spec. You must imagine that CH3 on the proton NMR is a singlet. You go for the proton NMR and look for a singlet. And then you start thinking, okay, I'm starting having a good idea of what do I have. But then you go back to the mass spec. What is 29? 29 is the loss of a particular group normally. Is an ether. So we know that we have an acetyl group. We know that we have a carbonyl. We know that we have an acetyl. Probably you should know already what molecules we're talking about. That's a very simple one. But you're not happy. You go back to the carbon. There is a certain number of peaks on the normal carbon 13. The first thing you should do is you have 4 carbons on the formula. You have 1, 2, 3, and 4 carbons, so there's no symmetry. All carbons are different. We saw that yesterday. Then you go to the duct. On the duct, one of the carbons disappear. It's a quaternary carbon. Look at the region. 170 is a carbonyl, probably not from a ketone. 170 normally you're supposed to have an halide or an ester. You don't have nitrogen. There is a very good chance it's an ester group. It disappears on the duct as a confirmation. What do you see also on the duct? You see something on the duct that becomes very, very useful. Methylene group. It goes upside down. You have a CH2. Aliphatic CH2 because it goes in this region below 60, which normally belongs to the aliphatic protons. Maybe there is something. This one is around 60. So you can think it might be connected to a strong electron withdrawing group, because to be an aliphatic is actually pushed at quite high frequencies. And then you have 2 groups here, 2 carbons here. That could be, they're both in the up phase. So it's either a CH or CH3, or there could be two CH3s, who knows? There could be one CH and one CH3, but you don't know. You will know after you combine all the different techniques and you know exactly what we're talking about. Look at the proton NMR. What do you see from the proton NMR? Apart from the singlet, that we can connect with the acetylene ion, with the acetyl group, that we know is there because of the mass spec. What are these two peaks normally? It's a CH3 and CH2. Are they coupled? You think? Yes, they are coupled. Triplet and quartet, looking at the very similar. Clearly, you cannot calculate perfectly the J from here, but you get an idea. These two groups are coupled one to another. Look at the integration now. You have 8 protons to take into account. So when you go for your report, on the proton NMR, you say, I see 3 different chemical environments on the proton. I have to fit 8 protons in total. From these curves, you can guess the distribution and the integration. I'm not going to give you proper numbers. I need you to reason on that. You have 8 protons. Look at these two. They look pretty similar. What's the integration of these 3 peaks? Considering we have 8 protons in total. 3 and 2. Okay, clearly this one, even without taking the ruler, you can see immediately that this one is slightly shorter than these two, and these two are practically the same. This is the curve it comes from the integration made by the instrument. Sometimes it's not exactly perfect, but if it looks pretty much the same, even if you take the software, maybe this one goes 3.1 and this one goes 3.0, that's still 3 and 3, because the integration sometimes, depending on the phase, is not perfect. Any idea what this molecule is? All considered. We have a carbonyl, which is not a ketone. You have 2 oxygen to accommodate in your molecule. One of the oxygen goes to the carbonyl. One of the other oxygen might be an ester. We know because of the position of this carbon. Is ethyl acetate. All considered. You have, if you have ethyl acetate, you have this combination. You have the singlet, which is the methyl group next to the carbonyl. You have the ester group. You don't have aromatic. Everything matches with the ion. This is how to calculate the degree of unsaturation. Okay. You want to write it down, otherwise we will give you. Yes.
What does it say? It's not really.
It's quite small because yes, I have to accommodate all the rest. But I'll give you in the slides, so don't worry. Basically, the degree of unsaturation, if you consider the normal compound as CaHb, and CODX stands for halogen or sometimes other atoms. Then the degree of saturation says that equals 2 plus 2A, so 2 plus 2 times the number of carbons minus the number of hydrogens gives you 1 more if you have 1 nitrogen, and you subtract any halogens. That tells you something as well. Oxygen, which is D, doesn't count in the calculation of the degree of unsaturation. So whenever you have oxygen, you discard it. It doesn't count. It doesn't add, it doesn't subtract anything. Instead, if you consider each of the halogen will substitute 1 proton. That's why you might remove it. And each of the nitrogen actually will add to 1 proton. That's why C is added. But anyway, I will give you this formula. So if you calculate for compound that we just had, C4, it means that it's 2 plus 2 by 8, which is 4, so 2 plus 8, minus 8, which is 8 is the number of protons that you have in the formula. And then that's it, divided by 2. That's it because you have 2 oxygen, but I say oxygen don't count in the cup when you calculate the degree of unsaturation. The only thing that counts in the degree of unsaturation are carbons, hydrogens, nitrogen, and halogen. Then you might say, if you can read it, don't worry, I will give you the slides. This is what you should say roughly. You don't need to write an essay of what you see on the each spectrum, but you might say at least name the most important group. On the AR, I can see they have a peak of 30,000, which normally correspond to aliphatic protons. The carbonite is a 1740. And at around 1240, it could be a C single bond O. This is the only thing you can tell me on this molecule from the IR point of view. Then you go for the mass spec. It's evident that we have an alkyl group of 43. That's typical. And probably you have a CH3, a CH2 of 29. Even if you don't see it immediately from the mass spec, if you don't remember that the 29 might come from the loss of the ethyl group, after you consider carbon and proton, and you know that you have the ethyl group, then you go back to the mass spec, and sometimes when you do this jump back and forth with different techniques, you can assign on the mass spec, for instance, peaks that at first you don't notice. Once you get an idea of the final molecule, then you go back to the mass spec and say, what if I remove this mass from the molecule? Does it correspond to any of the peaks that I actually need to consider? If it does, you go back to the mass spec and you add extra consideration. The more consideration you have, the more points eventually you get. But most importantly, the most consideration, the best consideration, and the most meaningful ones for each of the spectra that I'm going to give you really, really helps in the assignation of the final molecule. Because eventually, this is what you want to do in the lab. It's not getting 25 marks. In the lab, if you are looking for either for the characterization of an unknown molecule or the confirmation that you actually synthesize what you were supposed to, this is what you need to do. UV is no aromatic moieties. That's it. I can tell you normal is 1 mark. Don't miss it because it's an extra mark. But UV doesn't tell you much. Either there are aromatics or not. Carbon NMR, methylene from the deck, and 2 which are RSH3 or CH. From the carbon 30, I can see a carbonide, no other quaternary carbons. What you really need to remember, please, every time in the proper report, tell me I see that number of carbons, and you compare the number of carbons that you see on the carbon 13 to the number of carbons that you had in the formula. Sometimes happens that some of the carbons are overlapped. So if you have, let's say, 7 carbons and you see only 6, there is a chance that one of the 2 is overlapped, or the 2 of the carbons are equivalent. So there is some symmetry. Always consider all of them. On NMR, you can say that it shows a quartet coupled with a triplet, typical of CH3, CH2 next to each other. There is a singlet isolated at 2 ppm. The integration counts for all 8 protons. So again, like you always state the proper number of carbons, you always on the proton NMR take into account all the number of the whole protons. It has to match. It has to match. So if you are naming 2 signals, but it counts for 16 protons, there is something wrong. You have to try to consider the integration of each peak, the number of different chemical environment, which is number of signals. Then you count the multiplicity and proper coupling, and that everything should help you to understand what kind of molecule you have. Eventually, you write a little paragraph, all considered. Since you have a carbonyl, looks like linked to another oxygen, because the carbonyl group on the carbon 13 looks like, in the position of the carbonyl group looks like an ester. There are no other saturations allowed. One carbonyl is a carbon double bond oxygen. It counts for one unsaturation. There is also a carbon oxygen single bond. You know that from the IR. And the peak of the acetylenium ion on the mass spec, all consider the molecule should be ethyl acetate. This is a very quick report. And if you consider everything and you try to justify all the numbers which I'm highlighting, you will be able to practically, hopefully, assign all the molecules, because ethyl acetate is a very easy one. Let's go for this one instead. Think about it. And then, so what we're going to do today until 1 p.m. is going to be just exercises like that. Then we'll do next week, not this week. The workshop for this week is on the pericyclic reactions. The workshop next week is on this one. So, start thinking about it, then in 2 minutes we'll start discussing it, okay? I don't know for you, I know people will hate me when I say that, but this is, to me, is great fun. Doing this kind of stuff to me is fun. It's proper fun. It's like solving a puzzle. But apart from being fun, it's something that you have to do in a synthesis lab. Not matter if it's organic or inorganic. Even in organic, do NMR and carbon 13 to characterize the molecules. Yeah. On the left, because it's water. Any carbonyl is water, and it disappears. So any of the carbonyls have to disappear, along with any other potential quaternary carbon. Not doesn't matter if it's a carbonyl. Any quaternary carbon on the depth 135 disappears. So, for instance, look at this one. There is a carbonyl, most likely, it's over 200, and there is another one that disappears here. This is another quaternary carbon. You have to try to distinguish, to try to get a molecule that actually possesses this quaternary carbon, because it must be a quaternary carbon if it disappears on that. Must always 100%. Especially on the depth 1 to 5, quaternary carbon disappear. CH and CH3 go on the top. CH2 go on the at the bottom. All quaternary disappear is a rule. It has to be. So first thing you do, add the number of carbons and try to match with the number of carbons that you have, in case you might have some symmetry. On all these carbons, all the ones that stay on the depth possess some hydrogen. The one that don't have any hydrogen, quaternary, of course, of carbonates, because they are quaternary carbons. Quaternary carbons, they don't have to. You have to. So to start with, how many unsaturations we have here?
Five.
We'll say five. Five is correct. What do you think? Five unsaturations are quite a lot, but four might go almost instantly because of UV. It looks like we have an aromatic group. Remember that we didn't consider that so far, but you can have aromatic groups with 5-member rings. 5-member rings, one benzene ring has 4 unsaturation bonds. Let's say a pyrrole will have 3 of them. So we have to consider them all. The fact that you think you have an aromatic group doesn't mean that it has to be a benzene ring. No, normally it is. I'm not that mean. Normally it is. Okay. But 4 go for that aromatic ring. What's the other unsaturation? Clearly, the carbonyl. So you have all the unsaturations. You cannot put any more double bonds. Whatever creative you can be, please don't put in a double bonds because it doesn't match with the formula. So we have 2 magic numbers now in the mass spec. 2 of the recurrent numbers. I call them magic numbers because if you see them, you know immediately what they are. 43, we saw that already. Should be an acetal group, the acetylium ion. What's 91? The benzene with the metal, so the benzyl ion. So you are supposed to have, so what you normally do is, okay, from this one, I know that I must have CH3 linked with something. This one shows you might have linked with something. You have some aliphatic on the IR, but it's not that big. If you have a lot of CH3, CH2s, this peak normally is quite large, quite tall as well. Clearly have a carbonyl, but we didn't say what kind of carbonyl yet. What kind of carbonyl you think it is?
Ketone.
It could be a ketone. Why? Carbon NMR shows that it's very deshielded. That most likely is a ketone. We don't know yet, but you get an idea. So carbon NMR, you have 9 carbons in the formula. How many carbons you count on carbon 13? From that distance, it's difficult. I get it. Think about when you have a proper paper and you can really count them. Okay. It's difficult. Okay. Instead of counting the number of carbons, we'll think about it later. What can you tell me immediately from the carbon 13? Two quaternary carbons. Any carbon that disappears at the depth, it's a quaternary. So you have this little peak here, disappears here. This peak is a quaternary carbon. If you have an aromatic group and a subsequent on the aromatic group, that carbon where the subsequent is attached is a quaternary. So apart from the carbonyl, which is of course is the other quaternary, that this one must be one of those carbons where in the aromatic group where the subsequents are linked. Okay? So basically this one. This carbon. What's next? What do you have on the depth? The methylene group. And you have one CH or CH3. You don't know yet. What about proton NMR? Proton NMR, you have 10 protons to accommodate. Considering that you start from this side, try to do the integration. Once you distinguish the number, yeah. 5, you need to accommodate other 5. This one clearly is short. 2 and 3. You know that this one is a methylene group because of the carbon as well. You know that this one is a methylene group because of the pK91. So you see that you can cross-reference all the different techniques to understand exactly what you have at the end. So what's this molecule? Recap, 5 degrees on saturation, that was correct. FTIR 3000 and the carbonyl 1700-ish. Mass spec 43 and 91. That really tells you something. UV tells you that aromatics are present, so you get 1 mark if you say that. 113, 1 quaternary group and 1 carbonyl, which is also a quaternary, of course. 1 aliphatic and 1 methylene, which I said at the beginning. So when you put this one with the proton and MR, the fact that you have 1 peak which integrates 5, what does it tell you? It's a mono-substituted benzene. It has to be mono, so it means that you have 5 protons are all around and you have 1 substituent. Which of course you know also from the pK91. I'll consider. What's the molecule? Simple as that. Don't worry if you cannot put up a name on that. That's again easy enough. One side of the molecule. Really, one side of the molecule gives you pK91. The side of pK43. In this case, even just from the mass spec, you know, between the mass spec and the molecular formula, you have whatever you need. Okay. So don't lose easy marks. Even if you get from, let's say like in this case, even if you get the bright molecule, even just with 1 spectrum, go back, check all the other spectra, and add all the information that you need to have. More complicated. Oh, with this time we have a nitrogen. It's your free class. You do. Yeah. Yeah, I don't give you the UV here. UV tells you if there are aromatics or not. Can you tell me neither if there are aromatics or not? It's a 91, definitely aromatic, but especially because there's no need of UV. Remember this peak also. We discussed yesterday the fact that I can tell you if one of the peaks exchanges with the two, it's either coming from an amino group or an amide or from an alcohol. We don't have an oxygen here. It cannot be an alcohol. It has to come from NH something. So what can you tell me? Degree of unsaturation. I have 7 or 8. Who agrees with 7? 7. What can you tell me from the IR? What can you tell me from the IR? Anyone? For the people 3,300-ish. Well, we need to do the calculation. Try to build your molecule and then see if it counts with 7 on saturation.
Yeah, but I literally just round it up to +1, it gets to 7. I'll tell you minus 16, probably well to 7. I'm getting something this week. Minus 16. Wait, the legend comes on my
Go back to the spectrum.
There was 5 after that. Why is the
Which means remember that each cycle is an unsaturation. So benzene ring has 3 double bonds plus 1 cycle. That's why it's for unsaturation. If you have a cyclohexene saturated, that will count as one unsaturation. Try to do, if you want to prove it, try to do calculate using carbon and hydrogen with a cyclohexene, and you will see that if you input those into the unsaturation degree, the degree of unsaturation, it will count for 1 unsaturation. Each cycle is itself 1 unsaturation.
Each ring itself.
Each ring is 1 unsaturation. Yes, that's why each benzene ring is always immediately for unsaturation. Okay. Pica 91, we have the typical then we have this Pixa 106 is the previous fragment minus 15. Minus 15 normally, most likely is the loss of a methyl group from somewhere, not necessarily from the benzyl. Okay. Have a molecular ion. So what you can do is try to do a quick calculation with the formula and see if one of them is a molecular ion. If you have a molecular ion and it's quite visible, it means that the molecule itself is quite stable. We said that already on the mass spec. So the molecule is stable enough. When you have aromatics, normally the molecule is stable enough. Now, We have some CHs from the IR. You have NH something from the IR. You have aromatics. You don't have a carbonyl. Of course, you don't have a carbonyl. There is no oxygen. You don't know enough from the proton, from the IR and the mass spec. You don't know enough, but you know that you have the typical 91, which is the benzyl group. Plus, you have one fragment minus 15, which normally implies that you might have a CH3 somewhere that can be lost in mass spec conditions. Proton and carbon. You have 15 protons, which some exchange with D2O. Look at the integration. You have 15 protons to accommodate. 10 for 1. It could be. If you have 10 and you have a big multiplet here, because you cannot distinguish any proper multiplicity, splitting the one that tells you ortho para or beta substituted. What do you think this 10, integration of 10, considering you have aromatics? 2 benzyl rings. Each benzyl ring counts for 4 unsaturation. The total number of saturation must be 8, not 7. Sorry, never say 7. But don't worry, everybody makes mistakes in the calculation. We're not judging anyone, but at the exam, please be careful. Or retrospectively, if you eventually think I have 2 benzyl rings, each one counts for 4 unsaturation, and you got 7, you go back and you recheck your calculation, and maybe you find that it's actually 8. Don't worry. That's why you have all these techniques, not just one. You don't rely only on one of them. You have to cross-reference all of them to understand what kind of molecules you have. So you have ideally 4 and 5 and 1. One of them is a NH. This single peak on the IR shows you that that nitrogen-hydrogen bond probably has 1 proton only. That's a signature of that. All considered, 8 unsaturations. IR shows primary, non-primary, non-primary, so substituted amino group. It's not an amide because you don't have a carbonyl. It has to be NH something at some point in the molecule. So you sometimes you just put on one side, I must have an NH connected to something. Aromatic peaks at 1600-ish. Mass spec, 91 is the benzyl. That's it. You have the molecular ion at 197, shows that compound is quite easy to, quite stable. If you calculate 197, which is the molecular ion, minus 91, it gives you the peak at 106. Oh, come on. The peak at 106 here. If you do this one minus this one, it gives you another 91. So you have 1 peak at 91 plus another peak at 91. You can do those calculations retrospectively. Once you know that you have 2 aromatic moieties, probably pendant on both sides. Both of them must be aromatic moiety plus CH2 because of the benzyl. Carbon NMR. We didn't discuss too much about the carbon NMR. Let's go back. Carbon NMR shows you methyl, methylene, sorry, but no other CH or CH3 aliphatic. So all the other CHs are aromatic. One quaternary carbon that disappears, a large number of carbons, and a very small amount of peaks. That suggests symmetry, lots of symmetry. Okay. This quaternary peak is again probably the aromatic moiety. You can imagine if it's substituted, there is one quaternary carbon where the top part of the substituent is the aromatic ring. It's quite tall. It could be there are more. But especially the lack of peaks, considering that you have to accommodate 14 carbons, tells you that there is a huge amount of symmetry. So for these 10 protons, and these 4, what are these 4? And it's a singlet. It's all both CH2 of each of the benzyl fragments. So you have 2 benzyl fragments and something in between. Each benzyl fragment is how many protons? 7. You have to accommodate 15. 7 plus 7 makes 14, plus this one, get your 15. Okay. Always start counting the carbons and counting the proton environments. Then the proton environments, according to the number of total protons you have, suggest something as well. You have 15 protons, we have one large multiplet, and then 2 singlets, 3.6 and 1.6. This one, 1.6 is the one that actually substituted with deuterium, which suggests is the NH. So this molecule is actually quite simple. You see the symmetry? So it's so symmetrical that eventually you have 1, 2, 3, 4, 5 carbons only, basically. Yeah.
What is the last step when you've got that peak at 106? Is it from an NH rather than a CH3?
Considering that the isoelectronic, yes, it could be. But what you should consider in this case with the mass spec is that the peak of 91 and the molecular ion minus 106 gives you another 91. That's suspicious because 91 is a very, very stable fragment. That tells you that part of the molecule, which probably still has the NH attached, lost a benzyl ring, a benzyl group. But then, of course, the 15 does not necessarily mean loss of metal group. In this case, you don't have metal group, so you cannot have any loss of metal group. It has to come from the NH, which is in between. Happy? More questions? Go for this one. This is even more peculiar. This is the last exercise we'll do today. I will, there is probably, as far as I remember, there is another one, which is more difficult. Please do it at home. Don't look at the solutions first. Try to do it by yourself. As far as I remember, the last exercise is the most difficult of the whole set. Very doable, but more difficult.
Thank you.
That's it. Plain text.
Okay, we have that saturation. So. Four plus more than three. Now, two. What can you tell me from the IR? So on the formula, you have one nitrogen. IR tells you that probably you have some NHs. There's not a singlet. I mean, and IR is never a proper singlet, but let's say is a diverse NH. Is not exactly like the one that we saw before. What can you tell me from the IR, which is peculiar and which I highlight quite quickly? What's this one? What can this one be? In your knowledge of IR. Or we will see later. Probably will come up later with the whole consideration. Mass spec. Mass spec tells you only, this is one of the cases where mass spec tells you only something meaningful. All the rest probably can be calculated retrospectively once you get an idea of what molecule should be. Mass spec, the tip of mass spec here is, if I tell you the molecular ion is 83, but there is next to it a very large peak at 82, loss of one, what can it be? Loss of a proton, yes. So one loses a proton normally. On the mass spec, it's more difficult that the nitrogen loses a proton. There are two different compounds that on the mass spec are peculiar because they more easily lose a proton. One is the aldehyde. If you have an aldehyde, it's very likely that you see the mass spec -1. The what? Oh. Arrange means that there is an aliphatic that actually loses a proton. Aliphatics normally tend not to lose a proton on the mass spec. So there's something that, if you don't know exactly what it is, try to exclude something that cannot happen. So, okay, that's molecular ion -1 tells you something, which is very well connected to the peak of 2100 on the IR. It's not connected to the nitrogen. If you consider on the shape of the peak on the nitrogen, on the part of the amino on the IR, that tells you that it's probably a primary. And the primary don't lose a proton easily. So don't do carbon double bond nitrogen because it's unlikely. Okay, let's go for the carbon. Carbon 13. solvent, quaternary peak that disappears, 1, 2, and 3 different methylene groups. So you have 3 methylenes in the same molecule. Plus 1 CH that goes up. Maybe proton NMR will help you. 1 peak in exchanges with D2O, but I'm telling you this time, instead of giving it, because I'm generous, because instead of giving you the curves, which is probably going to mess up a little bit, I can give you the proper integration. For the one that shows exchange with D2O. What do you mean? 2 hydrogen on the nitrogen, yes. Or the one that exchanges with deuterium, he also integrates 2. It could be that the NH is a primary, but you should know already, or you can imagine already. You can go back to the IR and confirm. Use one or the other to confirm. From the IR, it looks like the typical shape of a primary amine, but also the fact that there are 2 protons. This integration that exchange with the 2 are 2 protons, not just 1. So it could be an NH2. What are the others? Yeah, 1, 2, 3, 4, 5, which integrates 2 with a triplet, which integrates 2 with a. It looks like a double triplet to me. If you're not sure, you say a multiplet. In this case, especially because it's square law, if you're not totally sure, you say it looks like a multiplet to me, or a complex signal, if you don't want to call it a multiplet. So you have 3 CH2, quite well, some of them quite well coupled one to another. 1 CH or CH3, because this one could be either a CH or CH3. It's quite tall to be a CH3. Quite high frequency to be a CH3. Normally CH3s, even when a CH3, even a methoxy, the one next to the oxygen, normally comes at 50, 55. They don't go much over that. This one is around 70. Any idea what the one that 2100 on the IR should be? It's an alkyne. Could it be an alkyne at least? How many saturations are on one alkyne? 2. How many saturation do you need to put? 2. You don't have any other unsaturations. All the rest have to be saturated. No rings, because one ring gives you an unsaturation, not other double bonds. All considered. This is the molecule you're looking for. That peak of 2100, quite sharp, really indicates an alkyne. But especially with the mass spec, -1, there are 2 compounds that easily lose 1 proton by mass spec. One is a halide, the other one is a terminal alkyne. That proton from the alkyne, the terminal one, is acidic enough, labile enough to be removed in the mass spec conditions. Otherwise, all the other protons normally are quite difficult to be removed in mass spec conditions. The NH2, yes, you knew about the NH2 because of the IR. The typical two shoulders shows that is a primary amine, not a secondary amine with 1 proton only attached. But also, you go back to that, you can confirm it with the proton NMR, like we were discussing here. Exchange it with D2O, but it gives you an integration of 2. So it's an NH2. If you have the alkyne, you calculate the unsaturation. It's 2 unsaturation. The alkyne is 2 unsaturation. All the rest has to be aliphatic. Carbon 13 gives you 3 CH2. We have 3 CH2. If you go back to the proton, they're all conjugated. One is a complex, let's say a complex signal. It should be a double triplet if you do it really, really well. If you're not sure, you say complex signal or multiplex. And it's the methyl group which is in the middle. And the other CH, which was very, very high, is the alkyne. It's a CH. It's too high to be a methyl. It has to be something else. You can confirm it with the IR. In this case, this is one of the cases in which the mass spec immediately, apart from the molecular ion -1, apart from that, doesn't tell you much. So you go back, once you use the other techniques to understand what is the molecule, you go back and you try to work it out. So once you establish it, then you go back and say, yeah, actually, M-55 works on 28. 28 is the loss of an ethyl group. So even if immediately doesn't tell you anything because it's not one of those recurrent numbers, you go back, you do your calculation, you have an idea of the molecule. There should be this long linear chain plus an alkyne, and you work out retrospectively, probably that molecular ion minus 55 is the loss of an ethyl group. If it doesn't tell you anything, you do the calculation retrospectively. It happens very often, especially because you have to be very careful. If you do at the very beginning and it's not telling you anything, you might get put off by that. You might decide that you have a molecule or a part of a molecule that is not there. So if you're not totally sure, leave it, work out the other spectra, and then you go back. That's the strategy that you should use to combine them all eventually to get the final molecule. Eventually, you write the all considered part. There are 5 carbons, 2 unsaturations. The 2 unsaturation, if you decided it was an alkyne, if you practice a little bit and you get a few of these exercises with alkynes, there are not many things that that go in that region. Another one that would have been a nitrile group, a C triple bond end, not double bond but triple bond end, but it's normally a little higher. It may go 2,300, and it's not that sharp. Normally, it's quite short. It's short and broad, the nitrile, whereas the alkyne, especially if there is a proton, is terminal, and there is a proton, is quite sharp. Not very high, not very intense like a carbonate, but normally it's quite sharp, very well defined. But only with practice. I'll stop here. I will leave you this one, which has a sulfur. That's the most difficult of the set. I'm pretty sure if you can do this one well by yourself, you're already in a good shape. But please use the other exercises from the field. The field gives you a huge amount of exercises you can practice. If you do, I wouldn't say not even half of them, you're absolutely sure to be spot on at the exam. Okay? So next week, Marcella will start for a month or so.